Swayam Prabha. Digital India. Educated India.
Hello and welcome to this session of the course Elements of Mechanical Vibrations. So, in the previous session we discussed how the orthogonality property of eigenvectors can be a powerful approach of decoupling the governing equations of motion, and hence computationally much more elegant and simpler way of solving the vibration response of a large degree of freedom system. So, in today's session we will take that further and understand how the orthogonality property and decoupling of the governing equations of motion simplifies the solution process for a multi degree of freedom system in the case of undamped vibratory system. We are now going to look at that if our equation of motion for let us say a free undamped system. So, we will bring in the damping little later just to keep things simpler at the moment. So, we are looking at free undamped system. So, our governing equation of motion is mq double dot plus k times q equal to 0, and then I can replace q double dot and pre-multiply the way we have done it in this way. So, now you have eta double dot. Please make a note, this eta double dot is still going to be function of time. It's is equal to 0, and that's of course we get identity matrix and eta double dot plus the spectral matrix into eta equal to 0. Now, let us look at one of the several equations. Please, you may realize this is n cross n, this is n cross 1. So, you have n decoupled set of equations, all of them are second order differential equations in the new coordinate eta. So, now if you take one of these n number of equations, each equation can be in general written. Let us say if we take rth mode and rth element in the diagonal in the matrix equation, then eta r double dot t plus the rth element here is going to be the squared natural frequency. So, pr square eta r t equal to 0. This equation is quite similar to your x double dot t plus omega n square x of t equal to 0. This is the simple single degree of freedom system. We are accustomed to see this equation as mx double dot plus kx equal to 0, but if you divide throughout by mass, this turns out to be this equation, right. So, this equation is now our standard form of the single degree of freedom system governing equation. So, the response is we all know how to find the response eta rt, and we know that there are couple of ways, but one way is to write the solution, general solution like x of t as equal to a cos omega n t plus b sin omega n t, or we can write this as c cos omega n t minus phi, which is going to represent the initial phase lag. So, one can use even the exponential form of the solution, but let us stick to this trigonometric form, and I will write the constant, arbitrary constant as CR to represent that it is the constant associated with the rth mode response. So CR cos PRT, we are representing the natural frequency now as P, and rth mode natural frequency is PR. So T minus phi R. This is how I represent the general solution to the equation number 1, exactly the way a single degree of freedom system response is represented. Now we know that we need to get the constants evaluated, right? The constants unknown are CR and phi R, isn't it? Other parameter like PR is already known for a given system. Okay, so when you do the eigenvalue analysis on the governing equations of motion, you already would be getting all the eigen vectors UR and all the natural frequencies PR by using the eigenvalue analysis, the solution process. What we are looking at is, once those modal parameters are known, how to find the response to initial excitation or initial conditions, or later on when we bring in the forcing term, how to find the response to forcing function as well. Okay, now we know to get the two arbitrary constants evaluated, we need two equations. So obviously the way we did it for the single degree of freedom system as well, we write the expression for the velocity. So now here you have minus CR sine, so CR and PR sine PRT minus phi R, isn't it? And then if we substitute or write for the initial condition at t is equal to 0, eta r 0 or not is what? CR cos phi r, and eta r dot at t is equal to 0 turns out as CR PR sin phi r, right? Okay, now I would write this equation in a form like this: eta r equal to CR cos phi r cos PRT plus CR sin phi r sin PRT. Okay. Yeah, and what is can we do we know the initial conditions like eta r naught in eta r naught dot? Do we know these as initial conditions? We don't. Why? Because these are principal coordinates. Okay, the initial conditions, like you pull the mass up and then release it, you are actually giving physical displacement to your physical system. So those displacements are like q, okay, q naught and q naught dot, that is the initial displacement and initial velocities of all the n masses that you can define physically, right? But the motion or the displacements in the principal coordinates is not something which is known, okay? But that should not bother us. Why? Because I can write now qt. We all know how this is written. Typically we write this qt, we know that this transformation was written as eta t, right? But we also know that this can be written in the summation form when r changes from 1 to the n degrees of freedom, and what we have is each mode or each eigenvector multiplied by the rth harmonic time function. You can show that if for example if you have the typical eigenvectors for a 2 degree of freedom system as a special case, I am just taking an example to highlight that point, is that suppose this is your first eigenvector, and then the second eigenvector is 1 minus 1. Okay, and then you have eta 1 t and eta 2 t, and your x1 t, that is the response of the first mass and of the second mass, was written like that, right? Now you can show that this is, when you do that multiplication, you can show that it does really turn out to be r equal to 1 to 2 u1 times eta 1, sorry, yeah, ur times eta rt, right? You can show that. You know, you can do that multiplication and show that this is indeed true. Okay, so instead of this, we will be using this summation series to represent the physical response. Okay, now there is specific advantage in the context of the way we are deriving this. R equal to 1 to n, and as this particular expression says that it is basically a summation, okay, into eta rt. Now we do not I mean, we need to replace this eta rt. Okay, now eta rt will be comprising these unknown constants which we need to find out. We have already got these two equations from the initial conditions, which can tell me that Cr cos phi r, this product itself, is eta r naught, and Cr sin phi r is 1 over Pr times eta r dot, okay, at time t is equal to 0. So this particular expression, I can get this as, you know, this is going to be Cr cos phi r. Now this Cr cos phi r is, I am replacing with eta r at t is equal to 0, and then I am left with cos prt. Okay, I am basically writing this equation now by replacing the Cr cos phi r and Cr sin phi r from by the expressions that I have got from the initial conditions. Then I have second term, which is this one, which is Cr sin phi r, which is 1 over Pr, okay, eta r dot at t is equal to 0 sin prt. This is what I have. Okay, now as we know, eta r naught, you do not know the value of it, you only know the value of q naught. Okay, so I have to somehow get q naught into the equation so that I can use the prescribed initial conditions on the physical coordinate. Okay, so how do I ensure that? I can do that by so I will do it this way. I can get this eta r, this equation, to write here that it is q dot t equal to r equal to 1 to n ur tilde eta dot r t. So we have two of these equations. Okay, now what I do is I pre-multiply both sides by ur transpose m q dot t. This is multiplying the left side by the product of these two quantities, and the same product will be on the right hand side, ur transpose m, and then you have this summation. Now you will wonder, why am I doing this? Okay, you will realize the trick. So just think about this, that when I multiply this product to each of the summation series terms, okay, this summation is a series from r equal to 1 to n, okay. So this will be like u1 tilde eta, sorry, this should have been r, u1 dot t plus u tilde 2 eta 2 dot t and so on, all the terms up to what, un eta n t. You agree with that? Now you are pre-multiplying each of these terms by this ur transpose m, right? Now ur transpose m multiplied by, let us say, first term here, what will be the value of this term? Recall what is your orthogonality conditions. The modal vectors are orthogonal to mass and stiffness matrix, okay, which means that ur transpose m us, okay, is equal to 0 for r not equal to s, and same happens, and same thing is true for the stiffness matrix. That means when two different eigenvectors are considered, they are orthogonal to the mass matrix and stiffness matrix. So which means that every term in this series will turn out to be 0 except when the term that corresponds to r, isn't it? Because ur tilde m ur is equal to 1 for orthonormal modal vectors. So ur tilde transpose m ur is equal to 1. This product is equal to mr when the modal vectors were not mass normalized, okay. Now they are all normalized. So ultimately this entire series on the right hand side and the product pre multiplication by ur tilde transpose m would eventually turn out to be eta r dot t, because only one term will be non-zero and that term will be equal to 1. So what you are left with is only eta r dot t, and it is quite simple to show that this particular expression is true for, sorry, it's true for the other initial condition, that is the displacement, that this is equal to eta r t. We can show that, okay. So what we are writing here are these two conditions that we have got: transpose m q dot t is equal to this. So this is 1 and this is 2, which means that if you substitute for t is equal to 0, I have eta r dot naught is equal to ur tilde transpose m q naught q dot at t is equal to 0. Similarly, eta r at t is equal to 0 turns out to be ur now you will soon realize where we are now heading to, having now got these two equations, which are very important from the point of view of application of the initial conditions. You know, the initial conditions are always prescribed on the physical coordinate q and q dot, okay. So these will be known to us because you will be actually physically giving some initial conditions to the system, whereas in this equation that we are writing, the general solution in the principal coordinates, the initial conditions required are these in the principal coordinates, okay. So now let us get back to this equation. We have um, now q of t ready with eta r naught and eta r naught dot getting replaced by the corresponding equations, right. So now just see that this summation series is simply now going to get slightly updated by replacing these quantities which we have got the expressions for. So now what I am going to write here is eta r naught, which is going to be u r tilde transpose m q at t is equal to 0. This expression is now replacing eta r naught, which is here, multiplied by cos p r t plus 1 over p r eta r naught dot, which is u r tilde transpose m q dot at t is equal to 0 sin p r t, and of course we should not forget the first term that we have here, which you can keep it here, and you can show that this works out well. Okay, what we wanted was the response, the free vibration response to initial conditions for this governing equation of motion of the system, which now has been obtained in terms of what? In terms of your modal parameters like your mass normalized eigenvectors, your physical input initial conditions, your mass matrix, your other modal parameter like PR, everything is known completely here. Okay, and so you have the response completely estimated. The beauty of this is it just involves matrix multiplication. There is no flimsy simultaneous solution of equations. This is all simple matrix multiplication. You can have a look at what are the sizes of these individual matrices. For example, what will be this size? N cross 1, sorry, 1 cross n, is it not? You can show that. So 1 cross n is your transpose of your rth modal vector. This is n cross n, this is n cross 1, your initial displacement multiplied by cos PRT. It's a harmonic time function, simple number here, and then again here you have the same thing happening here. So if this is the size, this is going to be a single number and added to this single number, and then this is all multiplied by your UR, which is what? N cross 1 vector. Okay, and on the left hand side what do you have? N cross 1 response vector to be obtained. So everything works out here perfectly fine. Now the nice thing here is that whether you are talking of 2 degree of freedom system or 100 degree of freedom system or 20,000 degrees of freedom, the process is exactly the same. You don't worry about the size of all these matrices, because you can simply write a small code in any platform that you feel like. What all you will need is your eigenvector matrix. Okay, so your U and the spectral matrix, which of course you have to get it from your eigenvalue analysis. Once eigenvalue analysis is done, the free or forced vibration response will follow through this with this route. What and how we have been able to find this out? Because we have a very standard way of finding out the response for a simple single degree of freedom equation of motion, and for using those equations and that process, we could we could do that because we were able to decouple all our coupled governing equations of motion through the modal transformation, right. We got all the physical coordinates transformed to a principal coordinate, which caused all these decoupling, and so things are very simple. Now you can realize, once you know and get the hang of the basics of a single degree of freedom system, solving many degrees of freedom is no big deal as such, in terms of I mean, of course it will involve computation time, but still you don't need to learn completely different way of solving the problem. It's all rooted to the solution process of a single degree of freedom system. That's of course for an undamped free vibration response, right. This is your response equation, and I would strongly suggest that you take small 2 degree of freedom system example, solve it the way we have solved conventionally, using assuming the solution, substituting it in those equations of motion, and getting slightly long expressions for each of them, and you solve it through this approach of modal analysis, and compare your results, right. And you can imagine that if that 2 degree of freedom system changes to even 5 or 6 degrees of freedom, it becomes too much of a computation. Okay, so this is computationally very efficient way of solving several coupled simultaneous differential equations in a little more efficient and nice manner. Okay, let's take a recap of what we discussed regarding the orthogonality of mode shapes. So the governing equation for a free undamped vibration system is given by this equation mq double dot plus kq equal to 0, and then assuming harmonic solution, the rest of the process we discussed clearly as to the fact that k into u equal to p squared mu becomes the modified form of the governing equation by substituting the assumed response, where this physical response qt is represented as an arbitrary constant times the harmonic time function. Now, if you solve this as an eigenvalue problem, the eigenvectors are given by u1, u2, and if it is an n degree of freedom system, you will have n eigenvalues, which are the squared natural frequencies, and n eigenvectors, which are arranged as column vectors in the overall eigenvector matrix. So then ui becomes the ith eigenvector, and that corresponds to ith eigenvalue pi. And now if we pre-multiply this equation, considering that you take only the rth mode eigenvector, that is ur. So in this particular equation, if you take only the rth modal vector ui, then the equation is given by this equation. Okay. And if you pre-multiply by us transpose, that means if this equation pertains to the rth mode, if it is pre-multiplied by sth mode, basically to suggest that it is multiplied by an eigenvector belonging to some other eigen frequency, then the equations turn out to be as you see in equation number 3 and equation number 4. This one is when you pre-multiply by us transpose, whereas the similar equation considering the sth eigenvector is pre-multiplied by ur transpose. That means the eigenvector corresponding to some other normal mode. So the equations now turn out to be these, and if we do some mathematical manipulation, considering or assuming that the stiffness and mass matrices are symmetric, so in such symmetric matrices, us transpose k ur is equal to ur transpose k us, and that way if you subtract equation 3 from 4 or vice versa, the equation that you obtain is this. Okay. This is something which we have already discussed. So, if this equation is further simplified by using the property that for a symmetric matrix you can flip the eigenvectors, and if that is the case, then this particular matrix on the left hand side or bracketed term on the left hand side turns out to be 0, and then you are left with the equation US transpose M U R into P r square minus P a square equal to 0. Now, with that condition, that equation is valid either when R is equal to S. In that case, most of the vibratory systems will have distinct eigenvalues, and so P r square minus P a square will be non-zero for R not equal to S. So, that means when you are considering two different eigenvectors and corresponding eigenvalues, P r square minus P a square will be non-zero, which actually means that this particular product will be equal to 0 for R not equal to S. So, these are the orthogonality conditions that we finally arrive at, that the mass matrix pre multiplied and post multiplied by two different eigenvectors, the product is equal to 0, and when they are multiplied by the same eigenvector pre multiplication and post multiplication will give a non-zero value, and that non-zero number is called as the generalized mass. That is what we have discussed, which actually is a statement of the orthogonality of eigenvector with respect to the mass matrix, and Mr is called as the generalized modal mass in the Rth mode. The same applies to the stiffness matrix, and then you get a generalized stiffness Kr as the outcome of pre multiplication and post multiplication by the same eigenvector, and it is quite straightforward to show that the Rth eigenvalue or Rth natural frequency is equal to square root of generalized stiffness and generalized mass in the Rth mode. Now, for the sake of convenience, we do normalize these mode shapes by dividing it by square root of the generalized mass in the Rth mode. So, UR tilde represents the mass normalized eigenvector, and it is equal to normalizing the original eigenvector by square root of multiplying it by 1 by square root of Mr. Now, when you do that, there is the reason why we do it is once we get these mass normalized eigenvectors and put them in a matrix which is called as the orthonormal modal matrix, U tilde, if you multiply and pre-multiply and post-multiply the mass matrix using the mass normalized modal matrix, it is quite simple and straightforward to show that the product turns out to be an identity matrix, because of the fact that when you pre and post multiply the mass matrix using the same eigenvector, the product is Mr. So, if you use mass normalized modal vector, the product will turn out to be 1. And then equally straightforward to show that the pre multiplication and post multiplication to the stiffness matrix will generate a diagonal matrix containing all the squared natural frequencies. So, let us say P r square, all the diagonal elements, because for any pre and post multiplication by eigenvectors which are different than you will generate 0 value. So, therefore, you can show that this multiplication will result either equal to 0 or equal to square root of the natural frequency. Now, the diagonal elements turns out to be square of the natural frequency. This matrix is also called a spectral matrix, and it will have the form as you can see here. Now, with this we are said to exploit this orthogonality property for solving a large degree of freedom governing equation of motion. So, what we say is that M and K are squares matrices, they are symmetric matrices, and the response in the physical coordinate is given by Qt. Now, we transform these physical response into modal or principal coordinate. So, that is done by expressing the physical response into summation of the response in the principal coordinates, and this has been already shown extrapolating what we learned for a 2 degree of freedom system, and this expression is can be also rewritten in a summation series, and we have also discussed how this is true. So, it is basically a summation of contributions from all the principal coordinates, and the contributing factors are basically your mass normalized modal vectors. So, their series, summation series, will give you the total physical response. Now, we have shown that by substituting these physical coordinates in its expansion into principal coordinates, the equation of motion, which is given by this equation number 1 in physical coordinates, can be converted into that in the principal coordinates, and pre-multiplying by u tilde transpose will give you this equation, which ultimately turns down into an equation given by 2, which actually shows that because of the fact that the vectors eta double dot and eta are pre-multiplied by diagonal matrices, clearly this entire equation 2 is going to be a decoupled set of equations. So, you have a diagonal matrix multiplied by q1 double dot, q2 double dot, and so on up to qn dot double dot, and spectral matrix again diagonal multiplied by q1, q2 up to qn equal to 0, which actually means that individual equation are only in terms of only one physical coordinate. Sorry, this should be eta 1 double dot, not q. Okay, this is yeah. So, this basically shows that each row of this matrix equation is independent of other principal coordinates. That means, the first row will give you the differential equation in eta 1, the second one will give eta 2 equation in eta 2, and so on. So, all the equations are given like this: p1 square eta 1 equal to 0, eta 2 double dot plus p2 square eta 2 equal to 0, and so on up to nth equation. Now, the advantage that we saw that such equation which is decoupled from other coordinates is quite straightforward to solve, and a standard expression for the solution exists from our single degree of freedom analysis. So, then it becomes very simple and straightforward to simply use our solution of single degree of freedom system to generate the response of a multi degree of freedom system. That is the biggest power of computational evaluation of the physical response of a large degree of freedom system. Solution of coupled differential equation is quite tedious, and when the degrees of freedom goes in thousands and lakhs, it can be almost computationally challenging to do. Now, how do we solve this? We had discussed that as well, that we assume the solution to be in a standard form which we used for a single degree of freedom system, some constant times cos p r t minus phi r, and then for initial conditions for this equation, these are the two initial conditions very well known. So, I will not get into the specifics of it, which we have already discussed. The idea here is to ensure that in the general solution, once you substitute the initial condition, we cannot use eta r naught or eta r naught dot, because the initial conditions are prescribed in the physical coordinates. So, therefore, what we do is, although eta r t in terms of initial conditions like eta r naught and eta r dot naught are in place, but we would like to somehow make sure that we represent the solution in terms of the initial conditions prescribed on the physical coordinates, which is q naught and q naught dot, and that process becomes simpler because we already know this expansion of the physical coordinate into the principal coordinates, and then what we simply do is pre-multiply this equation by ur tilde transpose m for getting the initial conditions. Now, when you substitute for t is equal to 0 in this equation, you basically have the left hand side as q naught and the right hand side as eta r naught. Rest of the things are the same, except that now because we are pre-multiplying the left hand side by ur transpose m, and similarly on the right hand side, one can show that this product is like this summation is in this type series going up to un tilde multiplied by eta n naught. Now, when you pre-multiply this entire bracket by this pre-multiplied product, only the product with ur tilde in this particular series will give you one value. Otherwise, from the orthogonality of the modal vectors to the mass matrix, we all know that when r is not equal to s, the product is equal to 0, which means that suppose this r is equal to 3, u3 transpose u1 is going to generate 0 value, which means that this term is going to be 0, this term is going to be 0, only one term will be non-zero and that will have a value equal to 1. So, ultimately the right hand side term is only going to give you eta r naught, okay. All other terms are going to be 0. You can check that out, right, which actually means that I have been able to now represent the initial condition eta r at t is equal to 0 in terms of the initial condition in the physical coordinate, okay. So, when you push the mass down as an initial condition, you are giving initial physical displacement to the system, vibratory system. You are not giving eta 1 naught, or eta 1 at t is equal to 0. Eta 1 actually physically does not exist in the scheme of things. So, therefore, the whole purpose here is to express the initial condition in the modal or a principal coordinate into the initial conditions in the physical coordinate. So, once we get this, this is the reason why we get that result, that eta r naught is going to be given by this. Okay. Now, on similar lines, if we take the time derivative of qt equal to summation of ur into eta r, you get this equation, and then the initial conditions to the velocity can be expressed now on similar lines using this expression. So, again eta r dot, that is the velocity in the principal coordinate at time t is equal to 0, is now expressed in this fashion in terms of the physical coordinate velocity. And once we use this these two equations which we have found into the equation, which is a general equation for the response, physical response, I can now replace eta r naught and eta r naught dot, taking them from these two equations 5 and 4, I finally get the response which is given by this. Now, you notice here that we have replaced these initial conditions in the principal coordinates into the physical coordinates. So, this equation is actually completely known to us, that it is comprising of a summation series contributed by each eigenvector, and each eigenvector is multiplied by this principal coordinate, and the contribution is determined by the initial conditions. In a 2 degree of freedom system, we discussed that depending upon how you excite your system initially, either the first mode will only contribute, or only the second mode will contribute, or both of those two will contribute together, right. So, this product and this product based on the initial conditions will contribute to the overall response, okay, general response. And because it is summation, which actually means that in general all modes will contribute, because this summation goes from r equal to 1 to n, that means P1 will also contribute, P2 will also contribute, P3 up to Pn will contribute, similarly from this particular term, right. So, depending upon what initial conditions you have given, if you have given both the velocity as well as initial displacement, then you will have sine term contributing, the cosine term contributing, the total response will get contributed from both of these two terms. And in addition, because it is a summation series comprising all the modes, so every mode will contribute. Now, the question will be, in some cases you would find that you may not give the initial displacement, only initial velocity, or you will give only initial displacement, not initial velocity. So, in that case either the cosine function or sine function will have its multiplying terms 0 or non-zero, depending upon how you excite it initially. This is how the total physical response will be obtained as a function of time. So, it is basically giving you the response in the physical coordinate, okay, as a function of time. Is there anything that is unknown here? You already will be prescribed how you are initially exciting your system. So, this is completely known, and also you should make a note that this q naught or q naught dot is actually a vector which comprises how your mass 1 gets initially moved, how mass 2 is initially moved, how mass 3 is initially moved, and how the nth mass is initially moved. Suppose there are 3 masses and you push only the first mass, or give initial velocity to only first mass, accordingly your q1, q2, q3, q4 will all be decided, okay. So, this is how the initial velocities are actually given, and even q naught will be comprising of the initial displacements at all the degrees of freedom. And then of course, based on that either all the modes will contribute or some specific modes will contribute, okay. Now, just to give you an example, if you take a beam and then say that this is like so many, you discretize it using this kind of multiple masses, and then if you push all of these in specific ratios upward and these downwards and then release it, the likely shape in which this beam is going to vibrate is going to be this, because you constrain the middle mass not to move. So, the most likely case is that it is going to be vibrating like that. That is the way initial condition will influence the way the vibratory system responds at any time t. Okay. So, we take a small example which is very important for you to now see how all these expressions that we have been writing, matrix equations, how they actually look like, and how the response to any degree of freedom can be obtained. So, this numerical example will slightly clarify what we learnt little bit better. So, I am taking an example which we highlighted once, that if you have a forging hammer having its anvil and a workpiece, isolated from a concrete block which itself is isolated from the ground in a way which is clearly shown here, and the hammer drops from a height. Okay. The hammer drops on this workpiece through a height, let us say if it is h, then the velocity with which it impacts on the workpiece, that we can be obtained using the height, right. Now, that becomes the initial condition for this entire mass. So, if we describe this as one mass, which is mass of the anvil here, and mass of this base, concrete base, is given by mb, and there are these stiffnesses, the stiffness of the anvil support and stiffness of the base support. So, ultimately this physical system is now transformed into a simplified 2 mass 2 degree of freedom system. The 2 degrees of freedom, right now we are constraining that it moves vertically up and down, that is it. Now, we are not considering other motions, just for the sake of simplifying the solution process. Makes sense also, if it is properly symmetrically located, any vertical excitation is largely going to generate a bounce motion. So, somehow based on the parameters, we say that, let us say as an example, the initial velocity imparted is equal to 1 meter per second. Now, if you use the data which is shown here, the initial conditions can easily be prescribed like this, because at the equilibrium condition, the anvil is sitting pretty, the concrete base is stationary in their own equilibrium positions, and you describe Q1 and Q2 as the physical responses about that mean equilibrium position. Okay. So, your initial displacements are 0. At time t is equal to 0, from where you would like to find out the vibratory response, the hammer drops on the anvil and imparts an initial velocity of 1 meter per second. So, your initial conditions for the entire system, q at t is equal to 0 can be prescribed as 0 0, because q1 is 0, q2 is 0, q2 dot is 0, but q1 dot is equal to v naught, the initial velocity with which the hammer drops on the anvil. Okay. We are assuming again that there is no rebound, the entire kinetic energy is instantly transmitted to the mass. So, with those assumptions, 1 0 becomes your initial velocity, and this is in a vector form. Just because there are 2 degrees of freedom, you have the vector of 2 cross 1 size. Okay. You can, based on our preliminary analysis, how to get the governing equation of motion, and in a matrix form you can formulate the mass and stiffness matrix. I think that is already done by us. So, the equation of motion will look like this, the corresponding mass matrix, the stiffness matrix will look like this. You can try it out yourself, and we have done that earlier. So, I am not going to discuss that again here. The response in the physical coordinate is going to be q1t and q2t, and that is how this qt vector looks like this. Okay. Now, if you substitute the k and m matrices with their parameter values in place, using all the values which are given in the previous slide, the equation of motion will turn out to be this. Okay. Now, you have numbers floating around, so you feel little comfortable in figuring out how the physical these matrix equation with numbers look like. Okay. Now, you may carry out the eigenvalue analysis, and you can use, as I have been saying, that there are many numerical methods and standard library functions available in many of the commercial software. So, either you can write your own numerical code for getting the eigenvalues and eigenvectors from a set of matrices, or if you are using some commercial software, you can actually use that to get the eigenvalues and eigenvectors. You can refer to their hub files to get that, and maybe we can show you some scripts how we can get those eigenvectors and eigenvalues. So, you will get an access to this software so that you can try it out yourself, finding out the eigenvalues and eigenvectors. We will make it available to you. The system natural frequencies can then be obtained, and through the analysis it is found that for these numbers or numerical values, the natural frequencies are as shown here. Okay. And the corresponding eigenvectors are shown over here. So, what basically it shows that if the mass of the anvil moves by 1 unit, the mass of the base will move by 0.89 units. That is in the first mode, both of them moving in the same direction. In the second mode, so this is your first mode, and that is the first eigenvector. The second mode, in the second mode, when the anvil moves down by 1 unit, the base moves up by 0.224 units. Okay. So, they are basically moving in out of phase. So, when this moves down like this and completes its harmonic motion, this one, the concrete base will move like this in the opposite sense. So, if this is moving down, this is moving up, but both of them completes their cycle of oscillation exactly in the same period, and that period is related to this value. So, 1 by this capital T is going to be 78.2 radians per second, sorry, hertz. Okay, 2 pi by T will, sorry, I must write this, 2 pi by T will give you 78.2 radians per second. Okay. That is what these numbers speak. Okay. So, we have these eigenvalues and these eigenvectors. So, basically U1 is actually 0.8911. These higher decimal digits are just retained there, because when we do some computation later, the rounding errors are less. Otherwise, those fourth digit decimal place makes relatively less sense. Okay. Now, these orthogonality properties we all know with respect to mass and stiffness matrix. It basically says that when R is not equal to S, right, then which actually means that when you pre-multiply this mass matrix, please make a note that this is your mass matrix. If you pre-multiply with, let us say, second eigenvector and post multiply by the first eigenvector, that means R is not equal to S. You can show that when you do that multiplication, turns out to be 0. Okay. You may not get exact 0 because of the rounding of errors, but you will be getting very close to 0. Okay. Look at that in relation to the numbers in the matrices. Okay. So, the product is nearly 0. If you use all the digits, maybe it will be almost 0. Okay. If this is equal to S, that means you multiply. So, this is the case with whatever permutation combination you use. Now, just we have 2 eigenvectors, first and second. So, now in this case, if you are pre-multiply by the transpose of the first eigenvector and post multiply with the second one, you still will get 0 or close to 0. Okay. But if you use the same eigenvectors, pre-multiplying and post multiplying by the same eigenvector, you can show that the number here is going to be non-zero clearly. Okay. So, even if you get that value as 0.5 or so, you look at that in comparison to this generalized mass. And similarly, if you choose some other eigenvector, but pre and post multiply by the same one, now in this case it is a second eigenvector that we are talking about, you again get a non-zero result. That is the orthogonality property with respect to the mass matrix. Okay. What you get by doing this, you basically get the modal masses. You get modal masses. So, the modal mass in the first mode is equal to this value, modal mass in the second mode is equal to this value. and now you know how to get the orthonormal or mass normalized modal vectors. How do you get that? So, you are, if you want to get mass normalized, you have to divide it by the rth square root of the rth generalized mass, is it not? So, if you divide, that means if I want to find out what is the mass normalized first modal vector, I will be dividing it by square root of 1.491 into 10 raised to power 4 and 1 0.8911. That is how I get the mass normalized modal vector, the first mode vector. Okay, same happens with the stiffness matrix. So, I am not going to discuss that, but you can verify it yourself that these are the modal stiffnesses, stiffness in the first mode, generalized stiffness in the first mode, in the second mode, and then you can similarly get the orthonormal modal matrix. That means modal matrix comprising mass normalized modal vectors. So, you can see that when you divide it by the square root of the first and second generalized masses in the respective eigenvectors, you now transform the earlier vectors into mass normalized eigenvectors. So, these are the two eigenvectors that you essentially get, and you can show then that if you pre-multiply your actual mass matrix by the transpose of the normalized modal matrix and then post multiply by the modal matrix, the product should give you an identity matrix, and that is what you will get, okay, the diagonal terms being equal to 1. That clear? So, this is basically essentially taking a recap of what we discussed in terms of the equations by taking a small example of a 2 cross 2. Although, if you write a small script in any language, okay, you can use the same approach to generate these parameters for maybe 100 by 100 matrix, and therefore, for 100 degrees of freedom or 100 masses representing your vibratory system. So, the process, once you understand for a smaller degree of freedom, you can simply extrapolate it for any number of degrees of freedom. And similarly, you will get the spectral matrix by pre and post multiplying the orthonormal modal matrix to the stiffness matrix, and as expected you get squared natural frequencies as the diagonal terms of the spectral matrix. We discussed this as a spectral matrix. Okay. Now, you can show that the square root of this will turn out to be the first eigen value, which I thought was something 70 something. Now, that you will get from this expression. Okay. Now, for this case of a forging hammer, let us find out that if the falling hammer generates the initial excitation to the anvil, how we can evaluate the response of the anvil. Okay. We will also find out the response of the base, by the process of evaluation, because once you write these equations, you get the response of all of your vibratory system components. So, it is not only the anvil, but you can get it for your base and for that matter all the n degrees of freedom of your system. And how do you get? Again, the baseline expression here is that we start with this expansion of the physical coordinates to generalized the principal coordinates, and when you write eta RT for the rth mode, the response in the rth mode is by the general solution of this vibratory response, considering eta r represents a decoupled system in the rth mode, you can write this, this is quite similar to writing Cr cos PRT minus phi r, right. This is the same expression written in a slightly different form, and we have discussed this in the foregoing slides as well. Now, what we do, we would like to replace eta r naught and eta r dot naught in terms of the physical initial conditions, right. And for that we already discussed that the physical initial conditions are prescribed, that means q naught is 0 0, that is prescribed because that is what your conditions of the displacement or response of the entire system was at t is equal to 0. Okay. So, you remember q naught as 0 0 at t is equal to 0, right. Then we use this equation which we have seen how we got that eta r naught is given by this, out of which q naught is given. So, basically eta 1 r is basically any arbitrary mode of the n degree of freedom system. So, eta 1, eta 2 both of them can be computed. In this case q naught being 0, you get eta 1 and eta 2 at t is equal to 0 equal to 0, right. That is the initial condition. But what happens when eta the q naught or q dot naught at t is equal to 0, q naught basically is given by this. This is the initial condition for the velocity term, right. Q dot is equal to 1 at the anvil and q dot is equal to 0 at the base. So, that gives you the vector 1 0 as q dot naught, and then when you pre-multiply by all this, eta 1 dot turns out to be this value, eta 2 dot will turn out to be this value, alright. What can you now do is replace this in the summation series eta r. So, eta 1 and eta 2 can be replaced because this is summation series, we will see how it expands, and eta 1 dot and eta 2 dot can be replaced by these numbers. You should make a note that if it is a 3 degree of freedom system, you would have got eta 3 0 and eta 3 dot 0. If it is n degree, I mean if it is a 10 degree of freedom, you will have eta 1 dot, eta 2 dot, eta 3 dot up to eta 10 dot. Okay, if I expand this summation series, turns out to be this. So, you can see that this entire expression is now in a summation series. I can separate it out, that is the reason why we took a 2 degree of freedom, so that you can explain each and every step clearly. So, what you have is the first modal vector u1 tilde multiplied by this term for r equal to 1. So, r equal to 1 means eta 1 naught, eta 1 dot naught, rest of these things instead of pr you will have p1 and so on. So, the first term is done. The second term will correspond to the second eigenvector u2 tilde multiplied by eta 2 dot naught and eta 2 dot naught and the corresponding harmonic time functions p2t and sine and cosine terms, right. That is the expansion of this general equation that we wrote. Now, what is unknown in this case? Nothing is unknown. You already know what is P1, you already know what is P2 from the eigenvalue analysis, you already know these initial conditions through these relations from the substitution of the physical initial conditions. So, actually you know everything here, you simply have to substitute and get the final response. So, if I substitute them, you can see that the normalized modal vector here of the first mode was found out to be this value and for that value. So, once you do that, substitute it, obviously q1 q naught being 0, eta 1 naught and eta 2 naught both of them are 0, and so you are left with only these this term and this term. But make a note here that even if q naught is 0, only cosine functions are going to be 0, okay, but there will be sine functions of both the modes. So, the modes which are contributing are both 23.33 radians per second first mode and 78.22 radians per second mode. So, if I write this equation by getting rid of the cosine terms here because of the multiplying a quantity being 0, then you are finally going to get this as your final response. Okay. it would be interesting to look at this expression from the perspective of realizing that how did you excite the system. That was a general excitation, no? It was not exciting it in a way that at t is equal to 0 a specific modal specific displacement ratios of the two masses were not maintained corresponding to any of the eigenvector. What I mean basically, that had you pressed the first mass and second mass in the ratio of the first eigenvector, you would find that this term will be equal to 0 and the response will only comprise of this particular part. Had you given one unit displacement of to the anvil and the base was moved by minus 0.28 or whatever that value was, then it was corresponding to the second mode shape. When you give that as an initial condition and then release, that means you are initially initially you are maintaining the displacement ratios of both the masses corresponding to the second mode and then releasing it. That will be maintained throughout and the first mode will not contribute. So, then you will get this term becoming 0 and this will be non-zero. And when both of them are not and you are giving arbitrary excitation, it is going to be this and this that is going to decide how much of first mode and how much of the second mode will contribute, and that will be governed by how much is your q naught and how much is your q naught dot. Okay. So, this is how the response can be evaluated, and what is the only unknown in this equation on the right hand side? See, q1 and q2 are basically the physical responses that you wanted to find anyways, right. So, q1t, if you if you take out the first term, that is the first row of this equation, you basically have on the right hand side of the equation a number, a function of time. Okay. So, the response of the first mass, that is your anvil, and the second row is going to give you the response of the base. Okay. The only unknown on the right hand side is time. So, if I want to plot, if I take different values of t, basically I am going to get the response of any one of the physical masses. So, q1t can be plotted as a function of time, and on similar lines I can plot q2t as a function of time. Okay. Now, from the design point of view, how do you make use of these responses? It is not only getting the response in one place, right. So, I have q2t now being plotted as time, whatever I do not know in which way it will be. So, this will also be of course periodic, comprising two frequencies. What do you make out of it? How I can use these responses finally in the design? Particularly many times we are concerned about the isolators, whether these isolators are going to be proper, because your machine is already designed, you may not be able to make any changes to the machine. It is only the supports that you have a choice of choosing appropriate springs or isolators. So, I can find out how much is q1 minus q2 as a function of time. What do you get by q1 minus q2? So, this is your q1, this is your q2, that is going to give you the dynamic stretch in the spring. How much is that spring is getting stretched and compressed, right. That also gives you the maximum force that is going to get into the bed, and if you know how much is maximum q2, that also will tell you how much is the force that is going in the ground. Okay. So, all these parameters you can use for ensuring that your mounts selected are going to behave properly, right. If these are helical coil springs, whether they will become solid, given the value of q1 minus q2 at any instant of time, given this kind of an excitation, okay. All of that basically then your input for iteration in the design process. Okay. So, these dynamic responses are never meant to be only calculated and then you start patting your back, right. So, it's meant to be ensuring that your design is sound and robust, right. So, this is how we have got. Now, as I said, if you had discretized any system into 10 masses, 10 degrees of freedom, the whole process remains the same. So, irrespective of the size of your matrix, the process is so straightforward, and look at what you are going to do. You are basically going to simply keep multiplying these parameters, these values. Okay. Once you get an eigenvalue matrix and eigenvector matrix, rest of the things are pretty much straightforward. There is no complex calculation involved except the initial eigenvalue analysis that will be required to get the modal parameters. So, this is the summary of this lecture. In essence, we understood the entire process of modal analysis for a undamped multi-degree of freedom system, and in the process we also understood how the approach of finding out the response, free vibration response of typical multi-degree of freedom system is in essence quite similar to that of a single degree of freedom system. And therefore, I must highlight here the importance and the relevance of studying the single degree of freedom systems in depth, in detail, because all of the concepts that we learn through a single degree of freedom system are basically extended and made use of in solving more complex and larger sized problems. So, these are couple of review questions for you. And these are the answers.